Thanks for attending this talk. This talk is not about robot, but autonomous driving. We're talking about simulation for autonomous driving, but the same idea or similar idea applies to robot as well. In fact, we're also working on simulation for robots. So there's lots of hope for autonomous driving. It has been there for many, many years, but until recently it becomes reality. This data is from 2023 from ARC Foundation. It specifies that the data shows that autonomous driving is safer than human drivers. For Tesla, FSD, the accident happens every 3 million miles. For average human person, the accident happens every 192,000 miles. So it looks like FSD back to 2023, 10 times safer than human driver. I really doubt about the data, but well, at least it's improving. That's one probably biggest reason that we are having very high hope for autonomous driving. The other, of course, is cheaper. According to the data, when we use horses, the average cost is $1.70 per mile. And then at the beginning of the 20th century, when Model T becomes reality, is the cost per every mile per mile is down to 70 cents. The same cost lasts for about 100 years. But now with autonomous driving, the cost of moving around will be reduced to 25 cents per mile. This is a huge improvement for people for transportation. It gave rise to a big market, for example, for ride hail. Ride hail nowadays, I think in Paris, I use Bolt in the last several days. It looks like it's probably in the city is $4 per mile, around that number. If the price is $4 per mile, then the market is about 4 billion. If we can use autonomous driving to reduce the cost, if we can reduce the cost for like 25 cents per mile, then the market will be $5 trillion. So it gave rise to a huge, huge market. So people have lots of hope on autonomous driving, but on the other hand, we need to pay attention to the reality as it's not that safe yet. Just consider the size of the software inside vehicles. Right now, for modern vehicles is 1,000 million lines of code. It's much, much larger than, for example, Space Shuttle, Boeing aircraft, Facebook. For example, Windows have about 50 million lines of code. It's much less than the software code in modern vehicle now. If we are using autonomous driving in the future, the lines of code will be 500 million lines of code. It's a huge software system. We know that we cannot prove the correctness of software. In industrial code, our average is like $7 per 1,000 lines of code. In that case, there are tons of code, tons of mistakes in autonomous driving systems. Well, in that case, can you rely on, can you give your life to this kind of machines? People start to have doubt. So we want to make sure that autonomous driving is safe. In that case, we have to use simulation because to test real vehicles on the road is very, very expensive. Similar for robots. If we train robots using real data, using the real equipment, it will be very expensive. For autonomous driving, if you test the real vehicles on road, it's about, I think, about $10 per mile. It's very expensive. This test, if also collect data, that's about the same cost. So if we use real world data, let's see. Do we? Oh, it disappears on the screen. Okay, so if we use real world data and real vehicles, then it will be very expensive to do this. If we collect data from the real world and then put the data in the simulator to do simulation not using the real vehicle but using their software systems, then the cost become much cheaper. But of course, if we can use simulator and the software for the vehicle, it will be very, very cheap. But the thing is that if we only use simulator and the software for the vehicle, will that consider a sufficient testing? Because now the data are synthesis data, not from the real world. Are the data good enough? Then there's a big question mark. But nevertheless, simulation is very, very important. It serves as a bridge between the real world data and the software systems for vehicles or for rollers. You can consider a simulator as a data amplifier. Because collect data from the real world is very expensive. If we can base on a small amount of data and then use simulation environment to enlarge, to amplify the data, to get synthesis the data for training and for testing of either autonomous systems or roller systems, that will be very efficient. So this is simulation environment for autonomous driving. You can see that there are many things we need to consider to make it realistic, right? So like the map of the city, the vehicles, the dynamic vehicles in the environment, and also, for example, here you can see the kinetics of the vehicle, right? So it has to be real. When it's drive on the curb, you need to feel the mass of the vehicle, right? So there should be the physics rules that to guard the environment, simulation environment. And for example, here the vehicle has to follow the traffic rules to make it real. So, and also it has the we have to produce large amount of data, so that we use like different kind of algorithm to produce this kind of data, whether it's dynamic or static environment, very quickly. And this is a demo of the system we have right now. Most of it open source. It's built on Kala, an open source platform. You can edit the map to put different kind of vehicle in the map. To configure sensors like lidar, camera around the vehicle. There's different cameras mounted on the vehicle. Front, rear, side. This is the lidar environment. To have synthesis 3D cloud, point cloud. This is a corner case that's produced by the simulator. This is to test the autonomous parking system. It produced lots of scenarios within the parking lot. Can be on the cloud, test multiple vehicles simultaneously, and this is for hardware in the loop testing. This is a demo of the simulation system. There are many things that need to be considered. For example, the physics-based simulation that has to simulate all the sensors on the vehicle. It's similar to robots. So here we have to consider different kind of camera, like fish air, different camera configuration. And also, because it has to simulate the real world scenario, then we did consider the camera is dirty. There are some, because the vehicle are moving, there the noises, there will be motion blur, etc., etc. And then for leader, same things. We have to consider different materials because it's always simulation, right? Just imagine that we put a leader in this room, then we need to compute what kind of 3D cloud it can produce. So that in this case, we need to consider like whether they're bricks or they're metal on the road. Even the direction of the leaves on the tree make a difference on the leader signals. All this has to be considered in a simulation environment. And here we do consider different styles that the style produced by the simulation environment in the virtual world may not be the same as the data collected from the real world. In that case, we have to do a style transfer using different algorithms. So here we do consider that the traffic has to be real. Like the NPC vehicles, it has to follow the style of human being. So this is actually what I'm going to talk in this presentation. And at the same time, we want to produce corner cases because for typical cases, we can collect on road easily. But for corner cases, it's very difficult to have real vehicle on the road to have corner cases. In that case, we can do this in simulation. The problem is that this corner case produced by simulator has to be real enough to reflect the real world. So this is the main topic today. So there are many different things we need to consider. The problem we try to solve is to make the physics rules happening in the virtual world. One of them is how to produce corner cases that looks real. There are some pre-work, for example, scenario generation, because we know that perception systems in robots in autonomous driving are empowered by technological leap in deep learning. But the thing that sometimes this deep neural network can be fooled by some scenario that it cannot handle. For example, this is work done by a professor at University of Chicago, UAOC, I don't remember, but they have this stop sign. If you put 4 tips on stop sign, for human eyes, they're still stop sign, but for this perception system, it can trick the perception system to consider this stop sign as a 45 miles per hour speed limit. For human, they're very different because for deep stop sign is right background with red background with white dot on top of it. But for 45 miles per hour speed limit is a white background with black 45 on top of it. It's very different, but however, for perception system, it can actually, with only this 4 tape on top of this stop sign, it can actually consider, for perception, you consider this as 45 miles per hour speed limit, and then vehicle won't stop. This is very dangerous. But this is only for static scenes. It's much harder to generate dynamic scenario that can lead to accidents of autonomous systems. There's some pre-work, but none of them are very successful. For example, this last work, this one, it can generate lots of accidents. But the accident, the problem is that it's not real. It produced lots of accidents for autonomous systems. You can see that they are front-to-front collision. It's really extremely rare. You can see on the road that you have 2 vehicles that has had front-to-front collision. Similarly, it produced lots of rear-to-rear collision. It's probably only happening in parking lots. On street is extremely rare that we have rear-to-rear collision. Similarly, we have this T-shape accidents is also almost never happening in the real world. So this generation of these rare cases, corner cases, is probably meaningless to test autonomous systems because they are not happening in the real world. Therefore, we want to have a system that we want to produce corner cases, but at the same time, these corner cases are real, they are natural. So we need a way to generate in simulator lots of different corner cases, lots of cases that lead to accident, but these cases are ranging from very, very natural to extremely not that happening in the real world. So we want to have a spectrum from these very natural cases. So these are the examples. The natural case is that we have illegal vehicle in green vehicles, right? They're driving on the roads at like 40 kilometers per hour. And the other NPC vehicles is driving at 50 kilometers per hour on a different lane. This is happening every day. It's very normal. We won't have these normal cases to test autonomous system whether they can drive normally, right? But on the other end of the spectrum, we have an extreme case that the ego vehicle in green is driving 40 kilometers per hour. And then there's an NPC vehicle suddenly smashed on the side of this green vehicle. Certainly this is an accident because we have a collision. But the thing is that, well, it is a collision, but neither autonomous driving system nor human can prevent this accident, right? You just drive on the road and then the other vehicle is driving much faster and smashing on the side of the vehicle. It's happening, but no, who can prevent this accident? It's happening, right? In the middle is cases that a little bit dangerous, but it's happening frequently. That the ego vehicle, you're driving at 40 kilometers per hour, but the other car is cutting in front of you, but it's driving slower than the ego vehicle. There are 50 meters between ego vehicle and the NPC vehicle. It's happening. We need to but whether this can cause accident of the autonomous system, we really want to test it. Now you see that there's a spectrum that ranging from very natural to very dangerous. There are lots of different scenarios in between, but we want to test all the cases to see whether the autonomous systems is safe or not. There are 2 challenges. The first challenge is how to quantify the quickness, criticalness, and the naturalness of the scenario. So now all these scenarios are produced by simulator, right? Then we want to quantify. It gave you a. You can imagine it's a short video. It's a scenario. It's a video, right? It's a video. Then you have to decide whether it's critical and whether it's natural. But the thing is that we have to find a way to quantify the naturalness and the criticalness of the scenario, whether it makes sense or not, right? So this is the first thing we need to consider. We designed a naturalness estimator and also a risk indicator to do this quantification. The second challenge is how to produce lots of scenarios that are diversified. We need to produce diversified scenario to test autonomous system, and this diversified scenario has to consider both naturalness and criticalness of the scenarios. So this is our system called on-demand scenario generation framework. The input to the system are real-world data. This real-world data, we learn from real-world data because this data from real world, they're happening. So these are the baseline to tell us that these data are from the real world, they're happening, so they are natural. And then we have a scenario specification. That's also input. It's called logical scenario. I'll explain in the next slide. So this scenario specification that the developer of the autonomous system have in their mind that I want to test this kind of scenario. This is a specification that, so for example, is on highway. There are around 20 vehicles on the highway. I want to test this scenario, this is in my mind, but I want the simulator to produce lots of similar scenarios. And this scenario has to be natural and critical. So these are the two inputs. Based on the inputs, we train naturalness estimator. So that we want to train an estimator that this estimator will guard how new scenarios can be generated. So like for example, we have data from the real world, we have 100 scenarios. These 100 scenarios are used to produce a model that to decide whether the newly generated, simulated, synthesized scenario are real or not. Based on this, we can produce probably 10,000 different kind of scenarios to do the test or to train the algorithm of autonomous system. And then we have risk indicator. Risk indicator based on how critical the scenario is. It's computed. This is not model. It's computed based on time to collision and number of collisions of the scenario that produced. So based on these two naturalness estimator and risk indicator, we have a risk intensify regulator to just decide whether scenario produced is real and also critical. And this is, we use a speciation-based search algorithm to produce lots of different synthesis scenarios. And these synthesis scenarios that satisfy the naturalness and risk indicator that this parameter are set by the users. And based on this, we produce lots of different synthesis scenario to do the testing and the training of the algorithm. And the scenarios, actually there are 3 levels of scenarios. The first is called functional scenario. Functional scenario is nothing but natural language description. Like, oh, I want a scenario with one ego vehicles on the right lane, and also 2 NPC vehicles on the left lane. On the left lane, one in front of me, the other is behind me. So this is a natural language description. You can see that it leads to a limited number of different scenarios. And then below it is a logical scenario. Logical scenario is our input. Logical scenario roughly specify, oh, I have NPC, I have an eco vehicle and two NPC vehicle on the left lane, to the left of me, and the other one is in front of me with a wrench, and the second NPC vehicle is behind me with 13 wrench. So it has some number with it, like, well, these NPC vehicles will cut in front of me with speed between, for example, 30 kilometers per hour and 60 kilometers per hour. So it specifies certain range. As you can see that the logical scenario has more specification than natural language. But the specification is between all the numbers are within a range, so there are actually also a limited number of scenarios corresponding to logical scenario. We need logical scenario because in most cases, the engineers of autonomous systems, they have something in their mind that they want to test. And this something in their mind, they're really difficult to get from the real world data. But for our systems, because we have simulator, we can produce anything the engineer wants in abundant of scenarios. And concrete scenario is a scenario with very, very specific, with very detailed number. So this concrete scenario, if we specify it, it can only correspond to one scenario. Like, for example, I have an ego vehicle that is driving at 17 meters per second. Two other ego NPC vehicles, one is driving at 30 meters per second, the other one is 15 meters per second. So it's very detailed specification that one with this concrete scenario, there's only one scenario correspond to it. If you have concrete scenario, you can only test only one scenario. But in most cases, for simulator, user wants one specification that can correspond. You can produce lots of different scenarios that's within the specification of the user. So in this case, we have real data set from GOSIM. GOSIM offers detailed vehicle trajectory from various locations in the United States. This is an open source data set, and also we have intersection and INDI. These are also open source data, not on highway but within the city. In this case, I won't go into detail of this algorithm, but we train based on the real data on mentionist estimator. So what we do is, based on the logical scenario from the user, we use the logical scenario to map to the real data. One logical scenario can get lots of real data, satisfy the requirements of specification of the user. And then, after we obtain the real data that satisfy the logical scenario, we train a naturalist estimator. So the naturalist estimator is to decide whether the newly generated scenario satisfy the real data. So its behavior, you can consider that behavior of the synthesis scenario is very similar to the one that happening in the real world. And this is a formula that we use as a reward function. You don't need to look into the detail, but we have two indicators, two sets of parameters here. One is for the corner cases, for the criticalness. That is adversary. So basically, it specifies, well, if the omega, so just look at the omega. If the omega is 1, then it's very dangerous scenario. Just as the previous slide, the other vehicle just smash into the ego, the NPC vehicle smash into the ego vehicle. There's nothing you can do. So this is very dangerous. So in this case, omega is 1. On the other spectrum, on the end of spectrum, omega is 0. I mean, it's very natural. It's happening every day. You're driving one ego vehicle is on the first lane and the other NPC vehicle on the other lane. It looks like no accident can happen. So in this case, omega is 0. Then user can specify the value of omega. If it's 0.5, it means it has certain criticalness, but it's also very natural on the road. So this serves as a reward function to produce different kind of scenario. And this is a scenario generation algorithm. We adopt a speciation-based particle swarm optimization algorithm. The reason we use this speciation-based algorithm is otherwise it produces too many scenarios that are very, very similar. Right? Because now we want the simulator to produce synthesis data to test and train the algorithm for autonomous driving. So if they are too similar, it's probably useless. Like for example, in one scenario, the ego vehicle is driving at 10 meters per second, and we produce another scenario that the ego vehicle is driving at 10.5 meters per second. It's probably useless. It's just too many waste computing resources. So we use speciation-based algorithm that can try to make it produce different kind of scenario that can be used to test autonomous driving. Then we do lots of experiments to say, oh, now user can specify whether I want very dangerous scenario or very natural scenario. We test our algorithms on different autonomous driving systems like Apollo. It's multimodal, mixed, different kind of modules that inside Apollo. And then we test recent end-to-end driving systems like TF++ and Interfuser, and also rule-based autonomous driving system, heavy agent and behavior agent. All these autonomous driving systems are open source. And we test on heavy scenarios and also intersection within the city. So here we spend lots of engineering work that integrate Apollo and Kala, these two open source systems. We noticed that most recent work are still using very obsolete Apollo version, like Apollo 7. But now the new version is actually Apollo 9. And also, typically, Apollo, in the empiric setting, in most papers of prior work, Apollo is integrated with LGSVL. LGSVL already stopped. So we developed a bridge between Kala and Apollo to make Apollo work with Kala. This very actively maintained open source simulator. So this is what we have that we integrate Apollo and Kala. So in this very nice Apollo setting, and this is of the setting of Apollo. This Kala and Apollo combined together, it produces a very nice environment to test autonomous driving systems. Then the question we try to answer is whether this can identify different kind of potential risk. Because what we imagine is that most accidents happen in the extreme cases. But what we found is actually in natural cases, there are actually also lots of different accidents happen for the autonomous systems. So this shows that there are some accidents actually happen only in very natural cases. So people are following their traffic rules, but actually it leads to accidents for autonomous systems. This kind of accidents probably are more dangerous because this shows that some autonomous systems, they are not considered typical cases. These typical cases can also lead to accidents, not only extreme cases. So this is the first experiments we have done. And this shows that we give scores. Remember here we quantify lots of things. We gave scores on safetyness of the autonomous systems. This also very interesting is that this shows that if we consider both safe cases, natural cases, and critical cases, the best performance is given by Apollo because it scores like, if you look at the yellow score, the blue one. Blue one approach achieves 80, a score of 85. It's much higher than the other systems. It's probably a correct conclusion because Apollo has been used not only in academia but also in industry for quite many years. It's probably safer than the other systems. If you look at, for example, heavy system, heavy agent achieve very score. If you look at yellow, 86 is very high, but this is a very, very natural cases because people, most drivers, most data on heavy they actually on heavy is probably people behave very normally. Only in the city there are lots of different things can happen. In this case, you can see that heavy agents, if you look at the red bar, it achieve very poorly in city environment. So this is same as what we expected. And then we test on different Apollo versions. If you look at Apollo version 7, is 74. And then if we go to Apollo 8, the score is much higher, 83. But from almost 84. But on Apollo 8 to 9, it's only improved a little bit to 85. And then we check indeed that Apollo 8 has lots of improvements. Like it fixed lots of bugs in Apollo 7 and add additional modules. So the safetiness of Apollo 8 is much higher than the 7. On the other hand, from 8 to 9, it only has code refactoring going on, so not only improve the architecture, but not so much about the bugs fixing and the new features added. So therefore, 9 safetiness is only a very, very minimum improvement over Apollo 8. So it demonstrates that our experience is accurate. So therefore, this is useful to have this on-demand scenario generation to test autonomous systems. And the second question is, can we control by using the parameter of omega? Can control the quickness and the naturalness of the scenario generated? And the data shows that, yeah, indeed, that if we increase the number of omega, the collision become it's more and more, right? And the average collision time dropped significantly. So this set of experiments shows that, yeah, if we just gave the omega between 0 and 1, we can produce either lots of corner cases or very natural scenarios that can be used to test autonomous driving. And the last one, there are lots of data here. You don't need to look into detail, but it shows that we found lots of bugs in different autonomous driving systems. So our synthesized scenario generated by our simulators can be used to test autonomous driving system and find real problems from these systems. So in conclusion, we found that this on-demand scenario generation framework is very useful. It can produce lots of synthesized scenarios that can find bugs from autonomous driving systems. And the synthesized data can be used to train algorithm for autonomous driving. Right now, we extend these systems to train robots and to find problems with robot algorithms. Yeah, that's all for my talk. Thank you.